So team, this is session 5. Basically, this is again inter-process communication part 3, shared memory. So shared memory, as you can understand, is some chunk of memory where multiple processes can write. So that's the quite simple logic. So ultimately, what do you expect in this session is how to create that memory, how the memory addresses can be passed to other processes, how can they write, how can we control these writing to the memory area by one process. So that's what you can expect in this and how other processes can access the same memory now. So introduction to shared memory, creating and configuring shared memory segments, quite simple now because you have done two examples, two techniques of inter-process communication. Therefore, you will find similarity in the calls, in the API, the buffer and the memory area, the pointers and that other identifiers and everything. So creating and configuring shared memory segments, using and protecting shared memory segments. Protection is very important because it is a common memory area where multiple processes will be using it, will be writing to it, will be reading from it. So we need to protect the access to this area. Definitely it has to be. And then locking and unlocking shared segments. Obviously, it is something like a database concept. When somebody is writing to it, others should be waiting. And when somebody is reading, others should be allowed to read. I mean the locking mechanism, what kind of locking we have. So here also we have to have that kind of concept here, locking and unlocking shared segments. Using the IPCS and IPCRM utility, the same command which we used in the previous section can be used to manage shared memory as well. Introduction. So the same concept. Shared memory allows two or more processes to share a chunk of memory. This is shared memory and this is process 1, process 2. Both are using the same chunk of memory. The address space for parent and child are independent here. Means it really does not matter which two these processes are. On GNU Linux, all processes have unique virtual address space, but shared memory API permits a process to attach to a common address segment, meaning common memory area where the details of shared memory are located. Let's create a shared memory segment, get an identifier for an existing one, and configure a segment, attach and detach, and some examples of processing using them, some processes using these shared memory segments. We need function prototype and symbols to be available for the application because the examples, learning by example is the best learning in my opinion, and I'm sure you are enjoying this learning where we are starting with examples directly after defining the concepts. So IPC.h and shared memory shm.h. So these are the two important files which we need to include. Sequence of steps would be first create a shared memory segment or use an already created shared memory segment, that is shmget. Attach the process to the already created shared memory segment, that is shm attach at. So get, attach, at, dt detach, and ctl control. So the functions query easy to learn: shm get, shm at, shm dt, shm ctl. Get, attach, detach, and control. So attach the process to already created shared memory segment with shm attach, detach and the process from already attached shared memory segment with shm dt, and control operations on shared memory segment using shm ctl. So these are the steps which we are going to use. in this program. The program is available under share session 5 folder, source shmcreate.c, and look at this example, quite simple. Include common.h where we are defining the details, main shmid, it is integer type identifier, and shmid is shmget. So we are creating the memory segment, create memory segment using my shmid, which is defined in common.h. If it is greater than 0, that means it is assigned, it is created, then created shared memory segment. And what we are doing, look at this carefully. I think it is quite self-explanatory now, because we have 2 3 examples, we have done 2 3 past topics which were more or less similar in concept. The SHM ID, the first was ID only, second was size, third was permission, and fourth is the flag, or what flag we are passing, that is IPC create, for example, here. So we use SHM get API function. We specify a unique shared memory ID, the size of the segment, and the set of flags. That's what, quite simple. Unique ID, size, and flags. The flag argument include both access permissions and a command to create the segment, that is IPC create, for example. That's the command which we are using here. So flag of argument, the permissions, for example, here we have access permission 0666. That is, first 6 is for honor, this is for group, and third is for others. And this is extra permission, which is set user ID, set group ID, and sticky bit. These are the permissions. So we are setting no special permission. 4 plus 2 6, that means read and write. For group, read and write. For others, read and write. For honor, all have read and write permissions. No execute permission to anybody. Getting information on shared memory, we can get information with shmctl API function. Let's first get the shared memory identifier from the segment using shmget API function. Once we have this, we can call shmctl to grab the current status of stats of the shared memory which was created. So shm shget get the size, retrieving information about shared memory segment. This is what you are going to understand in this program. Now we created that. This is another program which is getting the details of the shared memory book because we know the ID. So because we are using the same header file which is defining the common identifier. So we are using the same identifier, shmid, return value, struct shmds, that is data structure shmds. So this is the data structure where we are going to put the content from the shared memory. Shm memory set and the size of shmds. So the data structure of this SHM data structure, shared memory data structure, of that size, we are creating the address space, a buffer here. Now get the shared memory segment using the ID, SHM ID, SHM get my ID, and these are the values. Now we got the details into this SHM ID, and we can get the further details using this identifier. We can retrieve, or we can use smctl function, that is shared memory control function, on this ID which we have retrieved from SHM get, and then use this IPC stat. If you recollect, same IPC stat was used in previous session also, and the address is passed for the data structure where we are going to dump the value. So therefore this is what we are going to use, shmds in integer format and the shared memory segment. So we are printing the value, individual values. So the size of memory segment is %d, number of attaches are, that is defined by this structure shm attach. So what these possible value of this, what possible component of this data structure are, that we will look at the structure of this, the memory structure of the shared memory. Else control failed, CTL failed, and shared memory segment not found. If it is found, we are doing it. If else not found, quite simple logic. Let's understand line by line. If it was not clear right now. Let's understand again. To SHM control, we pass the identifier for the shared memory segment. The command to grab stats, that is IPC stat, and a buffer in which the data will be written from the shared memory. So we are passing the identifier, the command to grab the stats, that is a IPC stat, and the buffer where the data of the buffer will be written, data of the memory segment will be written. This buffer is structure of type shmid ds as defined in line number 9. So therefore it becomes important that we understand what all components are there in this data structure. Upon successful return of SHM control identified by a 0 return, we emit the data of interest. Obviously, what is interesting here is first we need to know what are the elements or variables in this structure. Here we emit the size of the shared memory segment, which is defined by SHM SEGSZ, that is segment size. Shared memory segment size. This is how you should read it. And the number of attaches that have been performed on the segment, and that is defined by SHM and attach, that is number of attach. So these are the two examples of the components which we will see in the structure. Obviously we are going to define and understand the structure, but yes, we are fetching these two details from the shared memory. Attaching to shared memory segment. Attaching maps the shared memory into our process's memory space. To attach to the segment, we use shmat API function, shm attach, shared memory attach API function. This returns a pointer to the segment in the process's address space. This address can be used by the process like any other memory reference. We detach from the memory segment using shmdt, that is shared memory detach API function. We will use a simple application to attach and detach from the shared memory segment, which will be using it. So attaching and detaching from the shared memory. We created one, we got the details and stats also. Now we are attaching and detaching the shared memory segment to a function given in shm attach.c program in session 5 folder under source. So same file common.h because it is where we have the ID of this defined. My SHM ID is defined under this. So integer main SHM ID and void memory area, get the shared memory segment using my SHM ID. So same thing, same function. If it is found, if it is greater than 0, attach the shared memory segment associated with this ID, and this is how we are attaching it. Memory equal to SHM80, and then printf. If it is attached, then it is attached successfully to our address space at this address, and detach it with shmdt if it is detached successfully detached. Otherwise memory detach failed or memory attach failed, and finally segment not found. That is logical flow. Let's understand one by one these calls. We first get the shared memory identifier using shmget, that is line number 11. Take note of this, line number 11. Then we attach the segment using shm attach shm80, which we are doing in line number 14. Then we specify our identifier, an address, an option word That is what we are specifying in this identifier. After checking if this was successful, we detach from the segment using shmdt, which we are using in line number 23. Writing to shared memory segment, we have attached, we have detached, but after attaching, if we have to write, if we were to use it, how can we write content to the shared memory? Because otherwise, basic operations we have understood: creating, attaching, detaching, controlling. But where is the real use? Real use is when we are writing something to it. So we need to write something to this memory segment. Only then the message will be passed, no, and only then other process will be attaching it and using it, what is there in the shared memory. So under session 5 folder source shmwrite.c, in this it's quite simple. We are attaching it and we are writing it. Let's see an example that uses string copy standard library function strcpy, and this is line number 19. String copy to this memory, and this is the content we are copying. So because this is what we have attached, SSM attached to this constant pointer null SHM ID, and to the memory area. Actually this is the memory area. We are defining a void memory pointer, void pointer to memory. Because we don't want to classify it as a type. There is no type, it is void type pointer. It is just a chunk of memory, so we can't give any integer or data type to it, but yes, it is a pointer. So to this pointer we are passing that pointer to write that content, and this is what we are doing. But then because it is a text, so we need to convert this pointer. This is a void type pointer. We need to typecast it so that it becomes character pointer. So character pointer memory, so our memory is converted to character type, and then we are using string copy to this memory. We are sending this data. That's a very quite simple and easy to understand string copy function, where the initially the memory was of type void, but when we are writing it, we are classifying it. We are saying that was this is not void type, this is a character pointer. So we are specifying a type here with typecast. Since the segment is just a block of memory, so we cast it. Typecasting is mandatory from a void pointer to a character pointer in order to write to it. That is the explanation I just give in line number 19. Reading from the shared memory, same way we can read also. So we are reading in line number 19 here, printf %s character pointer memory. So we are simply reading it. Of course, before reading, we are doing the rest of the process, getting the ID, then attaching it, and then we are reading from it. So now let's read from the block of memory by using printf call. The first process attaches to memory, writes the string, and then detaches it and exits. The next process attaches and reads from the memory. Removing shared memory segment. Now we have done all the operations: creation, getting stats, controlling, attaching, detaching, and putting content and reading content. Means our communication part is over. So we need the last step to remove it. So to permanently remove a shared memory segment, we use shmctl API function, same. So we use a special command with shmctl called IPC RMID. That is the interesting point, because same function, same thing, same detail. Only thing is that we pass this parameter as shm RMID. The way we passed shm stat, we are passing shm RMID. So this is a command called IPC RMID to remove the segment. Once the shared memory segment identifier is found, we call shmctl with IPC RMID argument to delete this. So let's understand, revisit the whole topic. This was a quick example, a walkthrough to make the concept clear. First, we understood from one figure what the shared memory area is, where more than one processes are accessing and using it. Then we gone through a sequence of steps of using shared memory area, creating it, controlling it, attaching, writing to it, detaching. So we got that, and reading and writing everything. So let's understand the whole concept now. The API have these functions: shmget, create new shared memory segment, get the identifier for an existing shared memory segment, shmctl, get info on a shared memory segment, set certain info on shared memory segment, remove a shared memory segment. Now if you recollect, get info was IPC underscore stat, remove was shm underscore that IPC underscore RMID. So shmctl have these commands. So get info, remove, or set info. SHM-AT means attach the shared memory segment. DT means detach the shared memory segment. So this SHM get API function. The SHM get API function is a multi-role function. It can be used to create a new shared memory segment, and second, it can get ID of an existing shared memory segment. So it can be used for both purposes. Create new shared memory segment and get the ID of an existing shared memory segment. The result of SHM get is an identifier that is to be used in all shared memory functions now onward after we have created it. So the identifier is the return, and we need to use it just like when we create a file, we create file identifier, and then we use that file identifier, for using and for writing and reading the data from the file and opening and closing that file. So we need these two header files, IPC and SHM. SHM get, this is a prototype. The key underscore T type key, size underscore T type size, and integer type flag. These are the three parameters we pass to this SHM get function. The key specify a system-wide identifier. It must be a non-zero value or a special symbol IPC private. Exactly same identifier. You go recollect that topic which we covered yesterday. Same was used. So identifier has a similar concept here on in the IPC. Non-zero value or special symbol IPC private. The size argument identify the size of same shared memory segment to create. And then when we are interested in existing shared memory segment, we leave this argument as 0, that we are not creating it. As a minimum, the size must be page size. Page size means the file system when we created it was the size of the page when we created the file system on this disk, on this partition. The page size should be the minimum, or 4 KB, depending on what is the page size. So SHM get API function, SHM flag argument, which was given the third argument, permit the specification of two separate parameters. One, a command, for example, IPC underscore RMID, IPC underscore stat, that was the command if you recollect, and optional set of access permissions 044 066, I think that was the access permissions were there. The command option can take one of these forms. Create a new shared memory segment with the SHM flag as IPC create, IPC stat, IPC create, IPC RMID. Remember these commands now. So IPC create will create it. This returns the identifier for the new or existing segment. If we want to create a segment and fail if the segment already exists, then we can use IPC create with IPC XL symbol. The same example we used in previous session as well. If you compare it, you'll find similarity, and I will give you enough time to compare enough time to understand both. I'm going to give you after the session at least 1 hour so that you visit, compare it, these examples with the previous example. You understand the difference between these two and the common nature of the calls and common nature of utilities we have, so that it becomes a one common topic, big topic of IPC. The third form simply request an existing shared memory segment. Shared memory segment permissions. When creating a new shared memory segment, each of the read write access permissions can be used except for execute permission. So same permission set, if you recollect the symbols, they were same used in a previous IPC also. User read permission, that is USR. R for read, user read, that's how you should read it. W for write, and G that for group. First is user group others. R for R for read, W for write, R for read, W for write. So now it becomes easy. User read, user write, group write, other write. So corresponding hexadecimal, oh sorry, octal values. These are the corresponding octal values. Examples of SHM get function. We have done one example, but now a specific example with these inputs. A new private shared memory segment of a 4 KB with all permissions to all, that is system, group and user. So SHM ID is equal to SHM get IPC private, because we are creating private. As we notice, there were two options in the first argument, either non-zero value or private special value. So first argument is that, second argument is size 4096, third argument is we are creating it, and fourth is not argument, is along with that command. Fourth is the permissions. And point to be noticed, in third there is no comma because it is one argument, the command and the permissions. Here we are separating them with comma. So this one, if you notice, no comma separation, it is space because it is a command in the permissions. So if the function fails, a -1 is returned with the actual error specified in error number variable of the system. Create a 64 KB memory segment with an error returned if the segment already exists. Our key is hexadecimal 123. So SHM ID, the value 123, 64 into 1024. So what is the learning here? You can give expression. IPC create, IPC excel. So we are providing multiple commands in parentheses with permissions. IPC create, and if segment already exists, then fail. So with this IPC EXCL. So now since we are using IPC EXCL, so we can use, if it fails, we can specify extra option also, or the command conditional logic also. If SHM ID equal to -1, segment failed. Shared memory structure, the SHMID DS, which I referred initially, that because we use the components of shared memory structure to put the data, to read the data, the how many attachments have been there and what is the size of it. We got two values, but there are more to it. So what all components, what all variables we define in the structure, SHMID DS. This is actually, we are trying to understand the structure which have this memory. So what all components we define in the chunk of memory. Obviously how many attachments we have is one, the size is another. So what all other components we have in this shared memory segment. A shared memory data structure that is contained within the kernel. What we have, this is the structure team. Carefully, IPC struct SHM ID data structure, and this has a structure IPC permissions, SHM permissions, that is access permissions, size in bytes, which is integer type, then last attached time, that is SHM attached time, time format. So three parameters are time only, last attach, last detach, last change. Then unsigned short integer, that is the process ID of the segment creator. So who created this? What is the process ID of the creator? Creator process ID, last segment user process ID, and then short SHM attach, number of current attaches. So this is these are the details of this. So current attaches, this is what we used in our example, and attach. If you notice, and we also use this size, SSM, SEZ, SAG, SZ, that is segment size. We use these in our example. So we could got more details also if we wanted. We using the including process ID and access time and attachment time and detach time. I challenge and I recommend, and this is the homework I'm giving you. You have to modify the existing program to use at least two more extra arguments to display the information, not in the first application, but after attaching and after putting the data and after attaching an application, you know, after attachment. So not immediately after creation, but after attaching and reading and writing to that during that process, I want you to fetch the detail. Means combine them three, four different programs to make it a better comprehensive program, and you will get enough time for this. This is the key type, what we specified. You notice key was also a structure. So in the key, what we have is key underscore t. So this is key we defined. It include user ID, group ID, CID, GID, CGID, CUID, mode, and this padding, sequence number. So these are all the details of this key which we specify. So key also has a lot of information. It is also a structure. It is not a simple integer type. After creation, the SHM-PERM structure is initialized with the key and creator's user ID and group ID. Shared memory data structure init. When you initialize, what happens on creation? Filled and initialization. SM, SHM SEZ segment size, the size of the provided. Attachment time, detachment time, C time, that is current time, C process ID, calling process ID, LPID, number of attaches. So these values are default. This is current time, this is current process ID, calling process ID, creator process ID, creator user ID, and group ID of the creators. So these are the memory data structures when you initialize the shared memory segment.